Chapter 11, Modern Atomic Theory. We're going to start with the hydrogen orbitals in 11.7 and talk about a wave mechanical model in 11.8 before discussing the electron arrangement. So let's start with the hydrogen orbitals. Orbitals do not have sharp boundaries. Chemists arbitrarily define an orbital size as the sphere that contains 90% of the total electron probability. The former school of thought said that there were electrons that were rotating around the nucleus, and they were similar to the patterns of the planets around the sun. And we don't think that anymore. What we think happens is that electrons are found within probability clouds that are surrounding the nucleus. And that's what an orbital actually is. Hydrogen energy levels. Hydrogen has discrete energy levels, and they're called principal energy levels, and we label these with whole numbers. So n equals 1 is principal energy level number 1, 2, 3, 4, and so on. Each principal energy level is divided into sublevels. They get labeled with numbers and letters, and they indicate the shape of the orbital. We're going to talk about those shapes in just a minute. This shows us a diagram that kind of helps us to see that, though. In principal energy level 1, which is the one closest to the nucleus, there's only one sublevel within that principal energy level. In principal energy level number 2, there are 2 sublevels. In 3, there are 3 sublevels. In 4, there are 4 sublevels. Within principal energy level number 2, we have the s orbital and we have the p orbital. And we're going to talk about what those are going to look like in just a minute. The s and the p types of sublevels. All right, so the s kind of looks like a sphere. And imagine that just going around with the nucleus right here in the middle. So we're just going to put a dot here. So the nucleus is right here in the middle, and your electrons are in this probability cloud here in the 1s. In energy level number 2, we have 2 sublevels. We have the s orbital, 2s orbital here with the nucleus. And then, if you can imagine the nucleus here, we're going to put that right here so you can think of where it would be. So we have the nucleus here, and the p sublevel looks a lot different than the s. While the s is spherical, the p sublevel looks like dumbbells. And you have to remember these are in 3D because we are on the x, y, and z axis in space. And so these blue areas are the probability regions for a p sublevel's electrons to be in. And that's what that stands for. So if you can imagine taking those and overlapping them, and then imagine the second principal energy level, the s, also being integrated within that. And inside of that is the principal energy level number 1. So let's look at how we label orbitals. The number tells us the principal energy level. The letter is going to tell the shape. So the s means spherical, p means 2-lobed orbital, x, y, or z subscript on a p orbital tells along which of the axis that it lies. So if you remember on the screen right before this, it showed the 2p and it said px, py, and pz because it's talking about which axis those are located on. The hydrogen orbitals are what we're going to look at now. So the question is, why does a hydrogen atom have so many orbitals and only one electron? The electron can only be in one area, one orbital at a time. So an orbital is a potential space for an electron, and atoms can have many potential orbitals. So what happens beyond the hydrogen atom? Well, the Bohr model was discarded because it doesn't apply to all atoms. Atoms beyond the hydrogen have an equal number of protons and electrons, and we need one more property to determine how the electrons are arranged. Now, in the hydrogen atom, there's only one electron, so whatever direction it's going is irrelevant. The spin on those that have more than one electron can cause a problem because electrons are opposite, want to spin opposite because they have the same charge. So you don't want one electron is not going to be near another electron, and they're moving at a high rate of speed. So we're going to talk about the spin. So they spin like a top. So while one's spinning this direction, the other is going to spin counterclockwise in order to avoid any attraction because they're going to repel each other at such a high rate. This leads us to what is known as Pauli's exclusion principle, which says an atomic orbital can hold only 2 electrons, and those 2 electrons must have opposite spins. The principal components of the wave mechanical model of the atom says, 1. Atoms have a series of energy levels called principal energy levels. That's the 1, 2, 3, 4, etc. The energy level increases as the value of n increases. So energy level 1 2, 3, as you go up, they have a higher level of energy. Each principal energy level contains one or more types of orbitals called sublevels, and the number of sublevels present in a given principal energy level equals n. So the n value is always used to label the orbitals of a given principal energy level and is followed by a letter that indicates the type or the shape of the orbital. So we may say 1s, meaning that it's principal energy level 1 with an S-shaped orbital, 3p, meaning that it's principal energy level 3 with a p-shaped orbital. An orbital can be empty or it can contain 1 or 2 electrons, but never more than that. If 2 electrons occupy the same orbital, they must have opposite spins because they're going to repel each other. The shape of an orbital does not indicate the details of electron movement. So what it's saying is I can tell you that it's an s or a p orbital, but that doesn't tell me where the electrons are because it's a probability cloud that they exist in or a probability region they exist in. So it indicates the probability distribution for an electron residing in that orbital. Let's look at a concept check. Which of the following statements best describes the movement of electrons in a p orbital? The electron movement cannot be exactly determined. The electrons move within the 2 lobes of the p, but never beyond. The electrons are concentrated at the center of the 2 lobes, or the electrons move along the outer surface of the p, similar to a figure 8 type of movement. And just to refresh your memory, you remember that the p orbitals are the ones that look like the dumbbells, and we have them on all 3 of the axes. The z-axis, and we would have it there as well. Okay, so that's what we're talking about. So which one of these makes the most sense? Remember, those probability regions are just that, regions of probability. And the example I talked about in class was if your parent came to find you in the school, do they expect you to be in the building? Yes, they do. Is there a possibility that you're outside of the building? There's always that possibility that you went down to the shop or something like that, or were on a field trip out to the pond. However, the probability that you're in the building is much higher than outside of the building, and there's a really good chance you are here on campus someplace. So that's what we're looking at. It's not a pinpoint. A probability isn't a pinpoint. So the correct answer for this one will be A, the electron movement cannot be exactly determined.